Okay, thank you very much, Chair, and thank you for the organizers for the invitation to come and participate both in the school and in CELMAC, of course. And thank you for the accommodation. But we tried at the school to show movies on the laptop from a Mac, and it didn't end up well. So I appreciate being able to use my own computer. So what I'm going to talk today about is some work that I've done, that we've done over the last several years, sort of summarized in a number of papers, talking about and looking at and applying the idea of a minimum energy configurations to the n-body problem and how we have to modify the n-body problem to actually make that a reality. So what we're motivated by, a fundamental question, is what's the expected configuration of a collection of self-gravitating grains? So as they attract each other, and as we'll find out, as they in fact rest upon each other, which is a little bit different for usual n-body problem studies. And the secondary question is, how do those configurations lead to the variety of small body, which means asteroids and cometary morphologies that we actually see in nature? Everything from highly bifurcated bodies to binary asteroids to everything in between. So this is really the fundamental motivation for the work that I'm talking about here, although you'll see that much of the work that we do at this level is much simpler than the arbitrary shapes that we have portrayed here. So what this introduces is the idea of a minimum energy celestial mechanics. And the study of celestial mechanics as applied to the dynamics of these, what we call rubble pile asteroids, leads to a somewhat non-traditional focus. So while these systems conserve angular momentum, they do not necessarily conserve energy because there are internal interactions due to surface forces and tidal distortions which dissipate not just small amounts of energy, but very large amounts of energy, and can bring the entire system down to lower and lower energy values. And specifically what we want to understand is how these celestial mechanics evolve to stable relative equilibria under this energy dissipation. But this is not a usual topic in the n-body problem, because in the formal n-body problem, there in fact are no energy minimizing equilibria for n greater than or equal to 3. And what that forces us to do is to add more realism to the problem through the inclusion or introduction of finite densities of these bodies. And I'll talk a bit more about this in the next few slides. One interesting aspect of this is that this automatically couples the rotational and the translational dynamics of the system together. So for celestial mechanics of point mass bodies, we know that a collection of these bodies will conserve angular momentum and energy. And here the configuration space is just the relative positions of these bodies. Their physical properties are solely described by their masses. And we just have the restriction that we can't have multiple bodies going towards a collision at the same time, signified by this. However, if we force this system to dissipate energy in some sense, it will actually eventually want to violate these conditions and then violate the existence of the solutions to these problems, and leads us to a very singular situation. So the very simple fix that we do is to add finite density to the n-body problem, modeling them as quasi-rigid bodies subject to surface forces and tidal distortions. We don't look at large-scale distortions, but we assume that there can be transfer of energy through small elastic deformations of these bodies. What this does, which is significant for us, is it enables resting equilibria to exist. Although it complicates the problem, of course, first in the configuration space, we need to worry not only about the relative positions of the bodies, but now the relative orientations as well. And I've just represented this here by a transformation matrix between the attitudes of two bodies. We also have, in addition to the masses, the moments of inertia or the inertia tensors that we need to worry about as well. One thing we do inherit is a lower bound on all the relative distances between these bodies, but that can be a function of the attitude of the bodies themselves. So this is the problem statement that we're actually dealing with. And for this problem, the system Lagrangian can be transformed into relative coordinates, and ultimately it's driven by an amended potential of the form given here, where h is the total angular momentum of magnitude of the system, which of course is a constant. I sub h is the system moment of inertia about that angular momentum vector, and that is not a constant, of course, as the body evolves. U is the mutual gravitational potential of the system, which can be complex in some cases. And then the total energy of the system is the kinetic plus this amended potential. And from this, we have essentially a zero velocity result that this amended potential is a lower bound on the total energy of the system. From this formulation, the relative equilibria and their energetic stability. And here, every time I talk about stability, I don't mean the spectral stability, such as what we have under the Routh criteria for the three-body problem for the Lagrangian solutions, but energetic stability, where I'm asking to actually minimize this amended potential so that it is, in fact, a minimum energy point of the system. So what we want to do is study the relative equilibria and their energetic stability. We analyze this, and we can analyze this through the study of this amended potential alone as a function of a minimal set of coordinates, q, chosen out of the configuration space, where in the most general sense there are up to 6n of these q, 6 for each body, because we have 3 positional and 3 orientational degrees of freedom. With this formulation as well, we can use the angular momentum as a parameter of the system, since this is nominally always conserved. So for the point mass problem, the study that we want to carry out is sort of defined as such. We have the amended potential, the moment of inertia relative to the total angular momentum is as such. The mutual potential is very simply stated. Equilibria are stationary values of this amended potential, and in fact, for all the appropriate coordinates, and since this has to hold true for all variations, in fact, we need each one of these gradients to be equal to 0. Stability, then, is just to study the second order variation of this amended potential at the equilibrium. And essentially, if it's positive definite, the system is stable. If it is not positive definite, it is not, because it cannot find or is not at a minimum energy configuration. And this is where the problem of just using point mass celestial mechanics arises. While the stability of the relative equilibria is always true for n equals 2, when in fact this is just the circular orbits, of course, it turns out to be never true for n greater than or equal to 3. All homographic solutions are always at a saddle point, if you will, of this amended potential surface. And this can be really shown by direct construction, that you can always choose a direction for the coordinates while conserving the angular momentum that both increases and decreases the energy function. This is nicely shown by some notes that Rick Mokel has. So under dissipation, the system will always approach singularity, and that actually doesn't work well for us. So for the finite density case, we really get to keep many of the same elements. The amended potential, the moment of inertia is just modified by now including the rotational moments of inertia as well, mapped into the appropriate space. The mutual potential is now generalized to an integral over these potentially complex shapes. And the equilibrium, we still have what we call unconstrained equilibria. But if you recall, since we now have these finite bodies with finite densities, there's always a minimum distance between which these two bodies can come to each other. And that provides the route towards another relative equilibrium condition. which is if we are actually at one of these constraints and the two bodies rest on each other, then the stability in the equilibrium, well, in fact, the equilibrium condition is just that the force holding these two bodies together should essentially act to hold these two, this coordinate to 0. And that turns out to be the stability condition as well. For the unconstrained degrees of freedom, we still need the variation of the energy function to be a positive definite. So under this system, under dissipation, as we decrease the total energy, the system will always approach a relative equilibrium because it can always end up resting on each other. One other view of this problem, and again, the most important differences between these two problems can really just be reduced to the properties of the amended potential and its relationship to the angular momentum and energy. For the point mass properties, the problem is that the amended potential is unbounded from below, as whenever any of those two particles get arbitrarily close to each other, of course, the energy goes off to minus infinity. And what that means is that there are no minimum energy configurations for n greater than or equal to 3, as any system can be construed to conserve angular momentum while driving that energy to minus infinity in a singularity. For the finite density problem, this amended potential under the restriction given here actually becomes compact and bounded. And that means that minimum energy configurations always exist for any n. And essentially correspond to the fact that the mutual potential is always bounded from below, and the moment of inertia is always bounded away from 0. So the study of this problem leads to, as I said, coupled orbit and rotational dynamics. And here I'm showing a quick movie. These are the same trajectories, but in general, I'll use the coordinates in the right. On the left, you actually have an inertial view. So this is what it would look like from, if you will, an observer sitting off an inertial space. And you see the orbital and rotational interaction of these two ellipsoids. On the right, I've actually chosen a coordinate frame that always lies along the centers of mass of these bodies and rotates with that rotation rate. So we see all the rotations relative to that point. And really what we're trying to do here, or what we're doing here, is studying the relative equilibria that can exist in systems such as this, and understanding how that may cause these systems to evolve if we allow the angular momentum to change, perhaps slowly over time, due to various non-gravitational effects. Now, in previous work, we've actually studied the problem of two ellipsoids resting and interacting with each other. What we're doing in this work is actually trying to push our way up to multiple bodies. And the easiest place to start is also the simplest, if you will, n-body problem with finite density. And that would be the spherical full three-body problem. And in terms of writing out the specific parameters of the system, the moment of inertia is the usual polar moment if we assume a planar system, and we just have to add in the moments of inertia of these three spheres with different masses. Probably the simplest aspect of it is that the mutual potential remains unchanged, so we don't need to worry about the difficulties involved with higher order mass distributions in the mutual potential calculation. The minimum distance between the bodies is very simple to codify. It's just greater than or equal to the sum of the radii. And all of these go into the amended potential. We introduce normalizations on the radii of the bodies and on the masses of these bodies, and these, of course, are connected with each other. And then what we can do, if we assume a specific ordering of these masses, so that 1 is the largest, followed by 2, followed by 3, is we can then completely study the problem just by focusing on this one triangle of the full parameter space of the system in terms of the mass 1, mass 2, and mass 3. So in fact, if we look at the system and study the relative equilibria and when they exist and what their stability are, we actually find some immediately interesting results. We all know, of course, that for the regular point mass three-body problem, there are only 5 relative equilibria: the Euler and the Lagrange. As soon as we have this finite density, however, we add 23 additional relative equilibria. And one way to quantify them are in terms of how many free degrees of freedom there are when we have different of these constraints in operation. So if we have 3 constraints in operation, we have no additional degrees of freedom left because the 3 bodies rest on each other, and that gives us a relative equilibria. If we allow for 1 degree of freedom where these 2 bodies can roll on each other, that gives us additional relative equilibria. Then we can separate these bodies, so we have 1 degree of freedom, which is the distance between the separated body and this body, and the other degree of freedom is the rotation of this body relative to that line. And then, of course, when none of the constraints are active, we have the full set of traditional equilibria solution. We can also order them like this, and here I've color-coded them so that green means that there are some value of angular momentum for which this configuration is stable for any combination of these mass parameters, M1, M2, and M3. Red means that these are always unstable for any mass distribution. And here we see some of the classes are always unstable, including, of course, the classical, which can be shown explicitly. And then there are some that sometimes are stable for some mass parameters and some angular momentum parameters. It's important to note, though, that none of these relative equilibria are actually stable across the whole range of angular momenta from 0 up to infinity. All of these relative equilibria are related to each other in some way or another through a bifurcation pathway as the total angular momentum is varied. None, in fact, are isolated by themselves. And the interesting connection to natural phenomena is that these bifurcation pathways can also represent stability transitions in so-called rubble pile asteroids. So that if you have a body consisting of boulders resting on each other, and if its angular momentum increases over time, and this happens due to non-gravitational effects, something called the Yorp effect, at some point the spin rate becomes large enough, or the angular momentum becomes large enough, that you can actually change stability of some of these relative equilibria, and one body can fall from a stable relative equilibria into an unstable one, and then the system evolves. What are especially significant are these transitions from a stable relative equilibria to an unstable relative equilibria. Because even though a stable relative equilibrium may disappear, there will always be some other stable relative equilibria for the system that it can evolve into, but that will always be at a lower energy. The 2 transitions that are most interesting are the transitions from a stable resting, and then under increasing angular momentum, you have an unstable system eventually. It spins so fast, so it must start moving apart. And then for the stacked or Euler resting configurations, these are always unstable at a slow rotation rate, but there was always a range of angular momentum where they will be stable, but then if you exceed or spin this too fast, at some point they always become unstable again. You can go through and precisely calculate the conditions. Here, this is looking at the Euler resting transition from a stable to unstable. Under this topology, there's only 1 degree of freedom that we need to worry about, and in fact it becomes very simple to work with the amended potential and come up with an explicit result for the level of angular momentum needed to stabilize this resting configuration. Similarly, we can study when this resting Lagrange configuration transitions from stable to unstable, coming up with some different criteria, and finally come up with a condition for when the Euler resting configuration actually becomes unstable and the 2 bodies want to separate from each other. So you can go through for all of the different relative equilibria and provide actually very simple analyses of what all these bifurcation points are as an arbitrary function of the masses of the system. And pulling all that work together, you can actually create these sort of comprehensive bifurcation charts for how all of these relative equilibria are related to each other. And it points out to us which of these transitions are the most interesting for looking for in terms of natural phenomena. So here, what we have plotted out is the bifurcation chart associated with this Euler resting configuration where you have the largest, the middle, and then the small. You could call this a snowman if you moved it by 90 degrees, right? And what we actually find is across the mass distribution parameters, we actually have different pathways that can occur. And the most significant one here is what happens when this resting configuration fissions. And in fact, it can either fission into this configuration where the large body is left and the two small bodies are separate, or it can also separate such that the two large bodies remain together and the small body separates. So this is a very complicated chart. If we just want to focus on that transition, we can represent that very easily in our canonical triangle, where this is M1 and this is M3, and this measures M2 again. And what we find is, depending on the values of M1 and M2 and M3, how this body, how the system fission actually changes. And in fact, there's a special line where this actually becomes a central configuration when you spin it at the appropriate rate. Maybe the most interesting sequence is the one involving the Lagrange resting configurations, because here we see, as angular momentum goes from 0 all the way up to infinity, that at every point there is always a stable relative equilibria that exists. And here we start off with the two resting configurations which are stable. At some point they spin too fast and they fission, but by that time we're guaranteed that at least this Euler aligned configuration, resting configuration, is stable. If this spins faster, when this fissions, we are guaranteed that one of these orbital configurations in fact exists. Now for this sequence, we notice that it always fissions in the same way when we have the smallest body in the center, which is the largest and smallest stay together, and the intermediate always separates from the system. This system also has one more unique aspect in that it actually can have a system where the Euler resting fissions into a stable relative equilibria. And that cannot happen for just two bodies. It only happens for very specific values of the parameters here. In fact, just this very small region down here. Otherwise, it always fissions into an unstable system, and in fact, it always fissions in this specific way. And we can also study the third Euler resting configuration. Again, this is unstable for low angular momentum, but stabilizes and then always has at least two stable members for high enough angular momentum. And here the dividing line for how it fissions cuts through the center of the system. And finally, to sort of complete the chart, we can also relate the orbital Lagrange solution to one of the resting isosceles solutions. And there are two possible bifurcation pathways that occurs there, but none of these are ever stable, so we don't really focus on those. So you saw that I was focusing on what happens when we lose stability from one of the resting configurations. And what generically happens, except for that very small parameter space, is the system immediately loses its equilibrium and it just starts undergoing dynamics. And these dynamics tend to be quite chaotic and energetic. And in terms of tidal interactions for these ellipsoidal cases, you can imagine that there are very strong tides acting between these bodies which will dissipate energy. Here in this three-body simulation, there's frictional forces between these bodies, what we actually see is that this system also dissipates energy and actually settles down, in this case, into one of these Euler resting configurations, or as on the pathway towards resting on that. Another thing to notice is that we can track the total energy of the system. And for the two-body problem, it turns out that if the total energy is negative, these two can never escape from each other. They're stable. They're Hill stable. If it's positive, it is possible for them to actually escape, even though the orbit currently is certainly nothing near a parabolic or hyperbolic orbit. But over time, you can actually transfer enough energy into the orbit from the rotation of the primary and to some level from the secondary, such that the system can disrupt. For the three-body problem, the situation becomes a little more complex, and is something that we've studied very recently with the paper in celestial mechanics. So now I'll talk a little bit about the Hill stability, or when is the motion in the system completely bounded relative to each other. As we know, in the point mass three-body problem, proving Hill stability is very difficult. And this is in part due to the unbounded amended potential. It doesn't provide us any constraint, although there are specific examples that come from CAM theory and the circular restricted three-body problem. For the finite density three-body problem, however, the conditions for Hill stability can be proven actually very easily for multiple situations. And this arises because the mutual potential between two bodies is now bounded from below, where we have this sum being the radii of those two spheres. So the mutual potential between any two bodies must be greater than this. And in terms of the amended potential, we note that if a specific body escapes, then all the relative distances to that body go to infinity. The moment of inertia goes to infinity. The mutual potentials with that body all go to zero. However, for the bodies that remain, they still stay finite. And the amended potential now approaches some finite value that's negative. Thus, if the energy is ever less than this summation, which is the lower bounds of these mutual potentials, then the body K can't escape. And bringing this to the three-body problem, if we assume this ordering, M3 less than M2 less than M1, it's extremely easy to prove these following results on Hill stability. If energy is small enough, all motion is bounded. As we increase it, first the smallest body can escape, then either the intermediate or the smallest can escape, then either one of these three bodies can escape, but only one of them. And finally, for positive energy, all of the bodies can mutually escape. Now, for the full body problems, however, it's certainly not a guarantee, because these bodies can also store energy in a rapid rotation. So if one of them happens to rotate rapidly enough, you can have a positive energy, even though the rest of the interactions don't lead to an escape. So it's certainly not a sufficient condition. A different approach to viewing the problem is to plot the angular momentum squared versus the amended potential value. And in fact, we can represent all of our relative equilibria on this chart. And here I'm doing it for specific mass values of 1/2, 1/3, and 1/6. And we can very simply come up with the energy constraints below which all the motion is bounded. Here, the smallest body is able to escape. Here, the two smallest can escape. Here, one of those bodies can escape, and it's only once we get a positive that all of them can mutually escape from each other. And here I have plotted the domain of existence of these relative equilibria when they're stable. So we can start off by looking at the resting configuration, which is stable down to 0. We spin it to a large enough angular momentum. For this mass distribution, this becomes unstable. And we see once that happens, it is possible for the smallest member of this system to be ejected. It doesn't mean that it happens. And we can actually plot these energy curves onto our triangular mass location. And what we see is when the bodies are roughly equal in size and they fission, and this is the energy when the system actually undergoes its fission, the motion will always be bounded. This is that first line which we've crossed. This is the parameter values that we're looking at in the previous plot. and you see how the other energy conditions arise. And it turns out always when in the lower right corner, where the main body dominates the system, that it's always possible, once fission occurs, for the entire system to disrupt. We can look at all the specific individual sequences related to here, that rotated snowman configuration. And again, we see once this fission occurs, here we're in the middle of this point here. The bounded region is smaller, and that's because the Euler resting configurations fission always at a higher energy than the Lagrange resting. And this is a more narrow region, but we still have the same qualitative distribution of hill stability depending on the mass distribution parameters. Here, the separate configuration, a very similar looking hill stability plot. And then the last one, and this one's similar again, although a little bit different. So this allows us to actually map out, as a function of how the mass is distributed within the system, what we expect the subsequent motion, or what could happen with the subsequent motion once the body actually spins to disruption. Here, this is a bit of an eye chart, but we see as we move across our different shapes and really the mass distributions for this three-body problem, we range from a situation here where everything is always bounded once it spins to fission for all relative equilibria, down to the corners here where actually when everything fissions, everything has a strongly positive energy and the system can completely disrupt. We find then a whole range of other criteria as we go through this, as we sort of explore through this mass distribution chart. So the current work that we're doing here is to expand this idea beyond just a simple three-body problem and start bringing it up to higher numbers of bodies and understand what pattern can emerge as we go to a more arbitrary value of n. And what I'm showing here are just the simplest study that we've done to date, where we can actually have very exact, where we can have exact results, which goes up to the n equals 5 problem, assuming that we have equal sized bodies that can rest on each other. And what we do here is we're looking at what happens to a system of n bodies and when and at what energies we can lose bodies from that collection if we increase the angular momentum and hence the energy of that system. So given these n bodies, I call a configuration is a collection of those bodies into p different groups, and each group having a set number of bodies. For the two-body system, this is simple. There are only two ways to order this: two bodies together or the two bodies separate. For the three-body system, there turns out there are three unique ways: the three bodies together, two together, one separate, and the three separate. And in fact, it's the sort of the integer partitions actually describe the sort of patterns that we can find as we go to higher and higher n. Up here for n equals 5, it turns out there are actually 7 different ways that we can partition the system. And these are important because the energy required for these systems to actually lose particles or become Hill unstable depend on how they're partitioned. And in fact, we can come up with these charts for energy limits for, here it's for 2, 3, and 4. The simplest case, we have the two resting configurations and the orbiting configurations. And if the energy is less than 0, these are always Hill stable. When we get to the right of this line, we lose the Hill stability. It doesn't mean that they must escape each other, but it means that they energetically have the possibility. For the three-body problem, it becomes a little more complex. For less than an energy of -1, and this is scaled for the equal mass case, all of these partitions can be Hill stable. Between -1 and 0, this orbital one is actually not Hill stable and can escape. And then again, when we get above 0, all of these partitions can in fact escape and are not Hill stable. Similarly, we can talk through it for the 4-body problem and ultimately for the 5-body problem, where we actually see a very interesting and sort of rich behavior of how the different configurations lose their Hill stability at very specific energy levels. Almost like a molecular system where if you increase the energy to a certain amount, you can have escape of the systems. And then what we're working on now is generalizing this to the N bodies resting on each other. The problem, of course, is that we lose the exactness because once we have more than 4 bodies that we want to pile onto each other, the topologies for that start to become more and more complicated to find the minimum energy configuration of that system. And we're also, of course, applying this to the similar fission dynamics for the 4-body problem as well as higher order problems. So just to conclude, the use of simple models, but accounting accurately for energy, angular momentum, and dynamical processes can be used to understand and elucidate the complex mechanics of asteroid fission and dynamical evolution. And what we're really striving to do here is to have a firmer mathematical basis for the analysis that we want to perform in the realm of planetary science, so that we can be confident about the conclusions that we want to draw from the natural world from our observations. In order to make that connection, we have to include additional effects such as cohesion, more arbitrary shapes, greater size diversity, size distributions, and the like. And each one of these changes can yield more realistic models, but if we try to understand them from the more mathematical side, it can also provide us a deeper understanding and continue to motivate our future research. So with that, I'm happy to take a few questions if I have time. Yes.
So we have 3 minutes for questions. So
Okay.
Please.
I have a question. During your talk, you used 2 different concepts of stability. One is stability with respect to variations of the position, and the other is Hill stability. But what about dynamical stability? So, for example, orbital stability or soft such motion. Is there a way of connecting these different concepts in an automatic way, or?
Yes, it can be. In fact, you can you can use the amended potential along with the equations of motion to evaluate what you could call the spectral stability or the linear stability of the system. And in fact, for the 3-body problem, if you satisfy the Routh criterion, then that's spectrally stable. But in that case, the amended potential is actually maximum. So that if you have any energy dissipation in that system, it should not survive. Now, for the libration, the Trojans and the like in the solar system, I think the dissipation is very small, so that you can treat as being very stable, completely stable. But for these very close-in systems that we look at, it turns out that as soon as you have the energy dissipation effects, those relative equilibria and that stability actually get destroyed, and they tend to move away from those relative equilibria. So you can connect it, but we've thrown that aside here.
So we have time for another question. If you are behind the column, I cannot see you. So if anyone on that side has a question.
Is there any relationship with what you are doing and the statistics of formation of binaries or triple system among stars? Have you tried?
Among stars?
Yes.
Because
I
haven't.
The fragmentation of something, and then you can have 1, 2, 3.
Yeah, I think that there must be connections. We haven't explored those because we're using this quasi-rigid body model, which is not valid, because there you get back into pretty fluid mechanics almost, because the bodies are very, they don't have friction in the inside, and they can achieve very different shapes. But yeah, and in fact, there is a field of the research that focuses on that sort of system and how you can have sequences, like the Jacobi ellipsoids, how they bifurcate once you add some additional properties to them, the instabilities and all that. So, yeah, there certainly is a connection.
Okay, maybe we can close here. Thank you very much.
Thank you.